Blind man don't blink, quiet man be quiet, wise man don't speak, pious man be heard. Go and branch your sheep, go and dig your holes and plant your seeds. Go and bridge your gaps, and if a tree sways, go and get your axe. Don't forget your roots, don't commit too fast to sell soul for soup and trade gold for glass. Some cast nets and some cast iron, some catch fish and some catch fire. They say that friendships never die, what a lie. Broke man don't break, money buys you power, won't give you strength, it won't bear your child or give you faith. When you get your cut, it won't fix your pain. You got deep roots. Try to hide it with a smile, but we know you got a sweet tooth. Yeah, me too. Rain clouds come and go, some bring life and some bring snow. They say that friendships never die, what a joke. Clever man, you tried to put me in a box, nice try, get a better plan. I keep a level head, I don't settle, never did measure me, you need steady hands. I done hit rock bottom, got a pen and drew a set of plans. What I built wasn't sand, so understand that I don't feel guilt. I know a tree without water gon' wilt. I know snakes in the grass keep rats out the garden. I know kids cry over spilled milk.
What is up, ladies and gentlemen? We are going to get things kicked off here in just a moment. I appreciate everybody being here. Thank you all for tuning in today. We have a very, very special occasion. The 1v1 event that we have all been waiting for. The True Earth debate live. Not the TikTok edition. Here we go. Things running just a little slower because of the change in format, so I appreciate you guys bearing with me. But we do have everything here ready to go. I do have our guest, Adam Everest, from the Mellowdome stream the other night. We will be discussing the true cosmology, evidence for and against our different positions. Let me go ahead and pull this up here. We do appreciate him coming on such short notice. Adam, welcome to the show, my friend. How are you doing today?
How's it going, man? Thank you for having me. Good, man.
Awesome, man. We got an exciting show today. Like, very, very exciting. I do have just a couple plugs that I want to make. Shout out a couple people that are in the chat. And, well, it's actually hard for me to do that without going on my phone, huh? New setup. I finally got the comments, you guys' comments, to be able to be read live over on the Rokfin. So, folks, if you are watching on the YouTube, go ahead and head on over to the Rokfin. You can make a free account, and you can chat it up, have your comments be read live. Awesome. So, with that being said, if you guys are about to enjoy this show without a bag of True Smacks, my friends, you are doing it very, very wrong. Not only are they delicious, nutritious, and organic, but they are very affordable, and they make you feel good after eating them. So go ahead and pick up your bag. You can use your promotion code SKY to get 10% off your order, and get them before they're gone, because I did hear through the grapevine that they were going out of business. It's a shame. So go ahead and pick those up. And while you're there, the true resource there is going to be their resource page. So go ahead and check out different experiments, links. You can learn about germ theory. You can learn about crypto. There's all kinds of great resources over there. So be sure to check it out over at truthsmacks.com. And on your way over there, you pass over your Play Store. Go ahead and download the Flat Earth, Sun, Moon, and Zodiac Clock app by Blue Water Bay. And use your referral code Tribune after downloading so they know that I sent you. That way you can be a blue dot, connect with other blue dots, and also get a ton of resources and bypass the YouTube algorithms and the Google algorithms that like to suppress this kind of valuable information. So with that being said, let's go ahead and roll on back. Adam, there was a lot that I wanted to discuss with you that I don't feel like we had a whole lot of time with that whole panel there. Things got really crazy. So I'm really thankful that you came on, that you can give us your undivided attention.
Absolutely, man.
For sure.
I feel the same way, man. There's just a lot. There was a lot that was covered, but just kind of a lot that got cut short.
Absolutely. Absolutely. So we are going to be going the first half, as everybody knows, the format. We do the first half of this show both on YouTube and on Rokfin. And then after the halfway mark, or whenever the heck we decide, 'cause who knows how long this show will go, we're going to go ahead and cut the stream over for the YouTube side. Nothing against you guys, but YouTube, their algorithms aren't that friendly. They don't do a whole lot of promoting. So I do like to go over to Rokfin where they do promote my stuff. So show them some love. And be sure to leave a comment so that we can all read it. Anyway, with that being said, I'll go ahead and ask you, Adam, did you want to open or did you want me to go first?
You can go first. It's your show. In the spirit
Awesome.
of things.
Yeah, no problem at all. No problem. Okay, so let's go ahead and just dive right in as usual. So the claim that we are on a spinning space ball flying through space at multiple different vectors at a predictable rate of curvature is not provable demonstrably. There's no empirical evidence for the claims, and there are actually plenty of evidence against the claims. So just to get right to the nitty gritty, I'm going to go ahead and go right to the curvature debunk. So the first thing I'm going to go ahead and bring up is the Mount Jacinto observation. And this is something that has been repeated. It's been done from multiple different angles. It's been done from 89 miles away. It's been done from 127 miles away. And the key thing here is that we're using infrared, which infrared really cuts through a bunch of the fog and haze. Contrary to popular belief, people do believe that infrared can actually cut through refraction as well. And unfortunately, that's just not the case. Refraction is when the light bends. It's not going to be able to straighten out that bended light. So just to go ahead and for anybody who may have been thinking that it can't see through refraction, but it can see through haze and fog. So that's something that's really important. But this picture was taken from, I believe, 127 miles away. It's actually really small for me to see, but it should be perfectly fine for everybody watching. And the height of the mountain is about 10,900 feet. Let me go ahead and elaborate on this. So they go ahead and do an analysis of the height of the different deltas, and they have the heights listed here. When you go into the Walter Bislin Earth Curvature Calculator, because I'm not going to pretend to be a mathematician, I've always relied on calculators. For better or for worse. And so I like to use a calculator that everybody can agree on. So the Walter Bislin calculator, let me go ahead and, now that I can, go ahead and pull this up. Now that I'm off the screen share. Awesome. Okay. So I got it pulled up, everything reset, perfect, no problem. We'll go ahead and do this math live. That way we can do something demonstrable. So, okay, so we got an observer height of 150 feet. Target distance is 127 miles. And the target size is 10,900. I'm giving it a couple hundred, I believe. Okay. And then let's go ahead and put that in. 150, 127, 10,900. Not trying to bore everybody with the math to spend too much time on it. Go ahead and calculate it for us. It's still saying 0 for the values, so I know that it hasn't done it yet.
What is the observer height?
150 feet.
Okay.
Oh, I see it. Okay, give me 1 second. I have to redo it. Awesome. Okay, observer height, 150 feet. You can do it along at the Walter Bislin. Are you familiar with that calculator?
Maybe. I've seen a few of them online, and then I was just using the one that is linked to Dave's app
Gotcha.
today.
Yeah, they're really fun to play with. Okay, so I got the number here, and it gives you a couple different values. I do feel like this calculator is superior if we're going to be talking about the math of the curvature, because it gives you all kinds of different values. It gives you the amount of the object hidden. It gives you the hidden angle, the drop angle, the refraction angle, relative horizon, the target top angle, and the sagitta, which is the bulge of water or land, whatever, how far you're measuring. So it does. I'm going to assume that it's doing the correct math. You're free to check it yourself with your own. And the bulge is 2,688 feet. The amount hidden is 8,368 feet. And the reason why that is because there's a lot of confusion around that hidden. And someone feel free to correct me if I'm wrong on this. But the reason why there's hidden is because we put in the actual observation, the object of observation, the size of that. And so there's going to be some geometry involved. It's obviously, if we're living on a sphere, it's going to angle away from us a little bit. And so, in any case, I'm not going to sit here and say that the whole entire mountain should be invisible. I'm getting a little bit of an echo there.
Sorry about that. I just pulled the feed up on YouTube so I can see what's going on.
Oh, no worries. In fact, let me go ahead and share my screen here for this, because I feel like this is pretty pertinent. Didn't realize I didn't have it up yet. Okay, my bad. Okay, so let me get back in here. You can see the values. Let me scroll back up so you can see here all the objects here that I put in. 150 feet observer height, 127 miles, 10,900. I do have it at 0 refraction. So we can play with that here in a minute if you'd like. But as you said before, when we're dealing with when we're dealing with massive objects and tons of missing feet, refraction's not really going to be able to help us with that. So let's go ahead and go back down here. You'll see the amount hidden is going to be 8,368 feet. And the bulge is going to be 2,688 feet. So because of the geometry of it, even though the bulge is only, roughly 3,000 feet, it's going to be able to hide 8,000 feet of this mountain. And that's also due to angular size. You'll see here it also calculates for angular size, top angle, all kinds of stuff. This calculator, the Globers consider this a superior calculator. So with that being said, let's go back to the observation. And you'll see here that this very bottom mountain, they have the peaks labeled out, and you can go and verify this for yourself, but we're able to see a peak that's like 4,000 feet, another one that's 7,000. And this image also is pretty interesting. It's being used to show compression that happens with things in a vast distance, which should be obvious. when things get compressed into the horizon so far. Obviously, there's some anomalies that happen with that. So you can see here's a delta of 300 feet, and then here's a delta of 600 feet, and they look almost the same just because of the compression that's going on over at the mountain there. So this is a mountain range. They're obviously different values, but in any case, I think that this is something that's really demonstrable. Let me go ahead and go back to the calculator for a moment. And I wanted to do this because where are we at? Let's get to that refraction here. And we're going to play with that number. Let's do standard refraction. It actually does it for us, 1.7. That's a bit large, but we'll give it to them. If that is the case, we still should have 6,763 feet of missing mountains. And yet, there they are on the horizon. So this only needs to happen one time to show that the horizon is not something physical. It's not a physical edge that we are seeing that's causing the sinking. It's actually something different. It's an optical effect. And to elaborate that, I do want to show this experiment that was done. A lot of people who watch this may already be familiar with it, but they actually show a real world example of what actually happens when you have refraction through a denser medium. And so let me go ahead and get that up for you guys. This will take just a second. Oh, wait, before I even do that, one more test that was done is the test over Rock Lake. This was 7.8 miles. The camera, I believe, was only 3 feet high, and the lights were 1 foot, and they were positioned a mile away. So I'm going to play this short little video just to kind of give some context so that you can I always recommend people do your own research and do the work yourself. And by the way, while I'm at it, I do want to give credit where credit is due. This image was actually taken by J. Tolan Media. And so if you haven't already, give them a sub. They are actually out there doing some field work, taking some observations, and bringing some stuff to the table. So we do appreciate that. Huge shout out. Let me go ahead and pull up this video for you guys. And I'm just going to let this play. That way you guys can get the full context. I'm going to shut up here, mute my mic, and I'll see you guys here in like 4 or 5 minutes. All right, so I think that should do it for that observation. Just to run by the play-by-play, just in case you missed some of it. 8 miles, 8 mile observation. They showed all of the lights in a line as if it was just getting smaller from perspective. Now, I know that the immediate follow-up is, well, of course, that is going to be refraction. So, give me 1 second here. Where the heck did it go? I need this up for a second. So the claim, of course, is going to be, well, refraction causes us to be able to see way further on the horizon. So let's actually take a real-world example and see what actually happens when we try to view this refraction in a controlled environment. So let me pull this up just 1 second. Awesome. I didn't even get to the salt and sea mirror test, but that's okay. I'm trying not to take forever. Okay, so this, I call it the laser fish tank experiment. Giving it a second to load. And what this does is basically this guy takes a...
Wow.
Hey.
Love ads. Get out of here. Love it. All right. The Flat Earth Science, the fish tank laser
We've heard it
experiment.
said time and time and time again.
Oop.
The farther away a boat is, the more the bottom of the boat will disappear, and you'll basically just see the mast of the boat.
If you send a ship straight to the horizon, eventually it begins to disappear until it's no longer visible beyond your horizon. Right. And you should ask yourself, what kind of surface would produce that result?
That wouldn't happen if the Earth were flat. You would simply see the boat getting...
Let's go ahead and skip ahead to the actual experiment.
Since the atmosphere is to reflect that light back to you. So yes, we live in an observable atmospheric gradient. Now take Snell's law into consideration here.
Let's imagine that I had a car. So let me draw a car. So we're looking at the top of the car. So this is the passenger compartment. It has 4 wheels on the car, looking at it from above. And let's say it's traveling on a road. It's traveling on a road. On a road, the tires can get good traction. The car can move pretty efficiently, and it's about to reach an interface. It's about to reach an interface where the road ends, and it will have to travel. It will have to travel on mud. It will have to travel on mud. Now, on mud, obviously, a tire's traction will not be as good. The car will not be able to travel as fast. So what's going to happen? Assuming that the steering wheel isn't telling it to turn or anything, the car would just go straight in this direction. But what happens?
Tanks, so you can see the light going straight. Next, I added a bunch of sugar to the water to create a gradient. Now I'm going to shine a laser through the 2 fish tanks, and you can watch that light bend downward toward the greater density. I also added some washcloths to the bottom of the tanks to help absorb the light and keep it from bouncing back up. Now let me show you what the boat looks like when the light gets refracted downward. Here our camera is in the exact same location as our control image, and now we are looking through a density gradient. Now here's a side-by-side to compare with our control image. With this, the first thing I want to point out is how much higher the bottom of the fish tank appears in our refracted image than it does in our control image. Next, I want to point out these yellow lines, which are exactly the same length. Please notice how the top of our refracted boat appears closer to the bottom of the fish tank in our refracted image than our control image. Here's a close-up for better comparison. And as you can see, the top of our refracted boat appears much lower than the top of our control image. This creates the effect that makes the boat appear to sink out on the horizon. So boats appearing to sink on the horizon don't prove that the Earth is curved. They only prove that we live within an atmospheric gradient.
All right, so I'm going to keep that one short and sweet. So that one was pretty straightforward. He can demonstrate that the light was bending downward like we would expect it to do in a dense gradient, and then shows you the active effect of what that looks like on things out on the horizon. So to me, it actually does appear to fit more with the flat Earth model than the globe Earth model. So let me go ahead and leave on one last note. And this note comes credit from Jeranism for quote mining this for us to be able to use. It comes from Scientific American, Thinking Globally, Acting Universally, October 1995. And this is from a famous cosmologist, George Ellis. He says, people need to be aware that there is a range of models that could explain the observations. For instance, I can construct for you a spherically symmetrical universe with Earth at its center, and you cannot disprove it based on the observations. You can only exclude it on philosophical grounds. In my view, there is absolutely nothing wrong in that. What I want to bring into the open is the fact that we are using philosophical criteria in choosing our models, and a lot of cosmology tries to hide that. Now, that last sentence to me is pretty damning, because if cosmology is a field of science, empirical study based on fact, reason, and the scientific method, then why would they be trying to hide anything? Especially something like the fact that they're choosing their model based on philosophical criteria instead of based on what the observations actually show. And not to get all wits it, but all the observational data does show that we're the center of the universe. So I'll go ahead and end on that point there. Let me go ahead and pass it back over to you, my friend. I appreciate you listening. I know I said we weren't going to take forever, and I kind of went on for a little bit there.
No, it's okay, man. I was watching and taking notes and just kind of trying to stay on board.
Absolutely. So I'll go ahead and leave it at that. And Adam, go ahead and take it away, my friend.
Okay. So I do have some questions based on the videos. So the first, or the first observation was Mount Jacinto. Yeah.
Yep.
So, and then we had, so I never knew what it was called, but what was it? The Sagita? Is that what it was called? Is that how
Sajida.
you pronounce it? Sagita? Okay. So I did a demonstration on Mellowdome, the last podcast, and all of my calculations line up exactly with that.
Amazing.
So I am glad that so when I did my calculations just now while you were showing the presentation, it lined up exactly with that. So I'd like to kind of present the math on that, and I promise it won't be boring if you're into the curvature, and then we can get into the next video and then the next video. And I think that I've already found common ground with you, so I think we're okay.
Nice. Yeah, if we can agree that our math lines up, then that'll save us a lot of time on the conversation. So I definitely
Yeah.
appreciate that.
So can I share my screen?
Yeah, go for it.
I'm gonna share. Okay. Can you guys see?
Yep, give it 1 second. Once you actually go, there it is.
Yeah. All right. So this was my initial presentation. I'm not very nervous right now. So if we take and we plug in some numbers, first I want to do the curvature of the Earth. So let me go here. So here's our 8 inches. Let me make sure I'm still working. 8 inches per mile square. Okay. So 8 inches per mile square is going to be, oh, I'm trying to zoom in. Oh, let me zoom. It's going to be based off of, let's say we're standing right here. This is going to shoot straight out. Okay. But the 8 inches per mile square, it's going to make the shape of a parabola. So it's going to come out like this. So the parabola, FMX said something on the podcast the other night that I completely agree with. The parabola, it works in favor of the flat Earth if you're looking at the mathematics in a two-dimensional plane. So when you have your sphere, it's just, this is 2D, so it's just a circle, okay? And this is a rough breakdown of what it would be broken down to. You have all of your right triangles here. And let me get back to my pen. You have all of your right triangles. So you have this one and this one. And then, so, and essentially what you do is you make two crosses. You cross corner to corner, corner to corner, centered and centered. And what that gives you is it gives you meeting points. And these meeting points are here. Oh, where's my pen again? Here, 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 and here. So we know that the distance from here to here is going to be the same distance. The distance of drop is going to be the same from here to here, right?
Sure.
So when we're drawing on a 2D plane, those are our initial plugins. Now, in our center point, God, why does it keep cutting my pen off? In our center point, we have our radius is from the center going up, and then we have a line that crosses, and that was that diagram that was on the other page, and I'll get into that in a second. So the 8 inches per mile square, you're looking straight. Oh my God, this is gonna drive me nuts. you're looking straight out, and it's off of this top line here. It's the amount that it's curving back from it. So over a 3,959 mile distance, it's going to drop 3,959 miles. Now that is also going to look something like that. You see what I'm saying? So this is actually rise, run, and slope. Okay, so this is a different triangle that gets drawn in. So we can calculate, and this is why I said the math, it's not wrong. So the curvature calculations, they're not wrong, but they're based off of drawing it off of a straight line and making everything curve in off of these lines. So when you're actually on the surface of a curved spherical object, it's a little bit different. And I'm going to try and demonstrate that with the other one. So let's say you're here, right? And it doesn't matter if I draw the line here or I draw the line here, as long as you have 2 points. So let's say that I am standing here, and whatever I'm looking at, the mountain is 127 miles away. Okay, so that is the distance. It actually gives you guys a little bit of extra playroom, because this is what's 127 miles away, and this ends up being shorter because the arc is always going to be longer than the chord. So, but just for the sake of keeping things simple and me not knowing trigonometry, I don't know how to calculate this arc. Okay, but I do know the chord. So if we know the chord and the drop height, then we can solve for a radius, right? If we know this distance here and this distance here, then we can solve for r. So, and I'll do a couple of quick demonstrations. So in order to solve for our arc for our chord length, we'll have to divide 127 into 2. So there'll be 63.5 here and 63.5 here. And the reason why it's divided into 2 is because this is the tallest point. This is the absolute tallest point right here. So that is where it's always going to be divided into 2 in this aspect, because you're going to look for the highest amount. So when we divide that, and then we have our known radius, or our assumed radius, so it's 3,959, which it's actually a little bit smaller, but it's okay. So if we multiply 63.5, and I'm going to use a calculator as well, 63.5 times 63.5, it's going to give us 4,032 and a quarter. Now we're going to divide this by the radius because we know the radius. So we're going to divide it by 3,959 divided by 3,959. That's going to give us 1.01, and then we're going to divide that by 2. And the number keeps going, but we'll save the hassle. Now this number will multiply times the mile, so 5,280 feet. And it's going to give us 2,688.84. Now remember, I rounded up, so if my number isn't exactly what theirs is, theirs was just 2,688. So if my number isn't exactly what theirs is, it's close enough to where it's not going to matter. So from this point up here to the bottom chord, there's going to be a 2,688 foot of hump. Now, why that's important is because if I take this out, okay, it's like cutting an orange. If I take that out, it's just like slicing an orange, and the slice is the part that we'll need to calculate for. So as long as this is gone from my feet to the foot of the mountain, it's completely straight. It's just straight. Now, once I add that back in, that's what's impeding my vision. So on the Earth curvature calculators, they are drawing it from a square, and they're assuming that not only are you looking straight out, but whatever's looking out at you, whatever you're looking at is looking out at you. And now there's just this empty space in here that it's not an accurate representation of what the horizon actually is when you're looking at the arc and the chord is what's extremely important. And if we know our chord and we know our radius, then we can figure what our drop is going to be, what our bulge is going to be. And I just learned that today. It's called you said it's called a Sagitta.
Yeah. Just think Dragon Ball Z, Vegeta.
Yeah. So, and then I will do one more demonstration on this just to kind of, so let's say that this was 127 miles, okay? And then what was our drop? 2,688 feet. So this is going to be 2,688, all right? And then we know that we assume that, so we'll do, okay, so we have our distance. So now we can solve, and we can do 63.5 times 63.5. Now, since we don't know the radius in this equation, we're trying to find what this is. So this is just cross-checking the math. Then we'll take that 4,032 and a quarter, and we'll divide it by the actual drop distance, by the bulge. So we're going to divide that by 2,688. That's going to give us 1.5, and then we'll have to divide that by 2. Wait a second. Hold on.
I think you doubled up on the dividing by 2. Long story short, are we in agreement with the amount that's supposed to be hidden?
Yes, as long as, so as if the peak is 10,900 feet, like of the mountain, right? That's going to be down here, or from the base of the mountain to the peak is 10,900 feet. So depending on if it's 150 foot, and we could do the math on that as well, you would just add in, but there should only be about like 8 something. Wait, let me see.
But so far, it looks like we're on the exact same page. Like, I'm not going to, because it looks so far like I'm in agreement with the math of what the Earth curve should be and what we should be seeing if the Earth is a ball.
So we should see around like 8,000 or so feet of the mountain. Does that make sense?
The reason why I don't think it makes sense is because you're in that calculation, you're not taking into account the angular size difference. So, although it is true that the mountain top, the tallest part of it is 10,900 feet at the most, the fact remains that 8,000 feet, based on the Walter Bislin Earth curvature calculator, which also got the drop right, probably got this right as well if it's accurate so far. And it's saying that because of the angle, so if you draw a line from the top of that, from the observer, the top of the observer to the top of the mountain, that bulge that's between them, although the bulge is only 2,688 feet, it's still going to be able to hide 8,000 feet of the mountain because the mountain has shrunk due to angular size. Not to mention it's angled away from you slightly because of its distance. I believe at that distance, it's angled away by like 2.5 degrees or something like that.
So if I'm 6 foot tall, okay? If I'm 6 foot tall, oh, that's my razor, sorry. And I'm standing here, and someone else that is 6 foot tall walks out 3 miles, okay? On the Earth curvature calculator, you should just be seeing their hair flapping in the wind, correct? It's a 72 inch, I think, at 3 miles.
Honestly, I don't remember exactly what it is. I know it's not as much as what people think at that small distance, but I'm not even really talking about that. I'm talking about the distance of because we brought up the Mount Jacinto observation. So I'm just trying to focus in on that. 127 miles. We got a 2,500-foot wall of water. It's supposed to be hiding about 8,000 feet of the mountain, yet we're able to see a delta that's only 4,000 feet high at its elevation, which means that there's about 4,000 or yeah, basically it looks to me like all the curvature's missing because the mountain is compressed. It's viewed from a distance. That's what happens when you zoom. So I'm just
Okay,
trying to find out
I
how.
will make one rebuttal on this, and it's because this is what helped me see this. So what I'm saying is, based on the calculations, there should be 8,000 feet showing
And
of the mountain.
I think that your calculation's incorrect. I think you're basing your calculation off of simply taking the bulge height and subtracting it from the height of the mountain. The problem with doing that is it in no way takes into account the angular size reduction, the thing that happens to the viewer. Your picture up there
Okay,
shows it in Muppet
so
vision, so it's a little hard for you to
explain
conceptualize.
to me what angular size reduction is.
Okay, so in the easiest terms, you see how my thumb's the size it is right now? As I move it back, you see it get smaller. As I move it forward, you see it get
I'm
bigger.
going.
Oh, I don't hear you anymore. I'll give him 1 second to come back on in. There he is. Short and sweet. So that one was pretty straightforward. He can demonstrate. We can hear the stream in the background, my friend.
Sorry.
Like we would expect. You're good. I see you're trying to pull back up that part of the show.
There we go. All right. Yeah, because it's from where I paused off on.
Right. So the thing that a lot of globers do is that they will take the height of the observation object and they will simply subtract it from the bulge. And some will even divide the bulge in half because they're like, well, that's the total length of the bulge, not the height of the bulge, even though that's not true. It is the height of the bulge. But the angular size is simply as objects move further away from you, they shrink in size as it appears to your eye. That's why the moon, even though we know the moon isn't the size of a hole in a piece of paper, you can still hold up a piece of paper at arm's length and look at the whole moon through the hole. That's what angular size is. So in your calculation, you're not taking into account the fact that that 11,000-foot mountain has actually shrunk and that 2,600-foot hump of water or hump of land is closer to you than the actual object. So it's going to appear closer to its actual size in reality. The thing is that in the observation that I'm pulling up, we're not seeing the curvature at all. We're seeing the mountain shrunk due to angular size. We're seeing the city laid out in front of it also shrunk due to angular size. But we're not seeing the actual drop that we're supposed to be seeing. We're still seeing the whole mountain. Maybe give or take like a thin little strip. I'm not going to say we can zoom. I can't zoom in on an ant at the base of the mountain, but we know that as things get further away, there's also something called Riley's principle that you may not be familiar with. But basically, what happens is things towards trying to think of the exact word for it. But basically, there's an angle of can't remember the name. I'm brain farting on it. Basically, your viewing angle also determines how much that you can see. And that angle changes the further out you get, and this can be easily demonstrated. So what I'm trying to say is if we can agree on the math and we can agree that there's, even if we take it all the way down to 2,600 feet of missing mountain, we're just not seeing that. So I wonder what your response would be to that.
So I think for it's oh, I'm sorry, I'm still looking at this. I think for the angular, what did you call it? The angular
size or angular resolution? I can't remember which one it is. I think
Okay.
it's angular size.
So for the angular resolution, I'm trying to understand how and I really am. I'm trying to understand, like, as you're talking, I'm just trying to picture it in my head, and I understand what you're talking about. So it shrinks down, but the actual size of what you're looking at, it's all shrinking at the same rate. So it's not like it's going to make it shrink behind. It's not physically shrinking. It's optically shrinking because of the distance that you are away from it.
Yes
So
and no.
you'll still see you'll still see the whatever's supposed to be seen at your perspective height. You'll still be able to see it. It's just in a wider view. So it shrinks to perspective, but everything that still should be seen in that, in that perspective is still in the picture. It's in the image.
So I actually agree with you. When you zoom in, you can see the whole mountain, even though the mountain has physically shrunk due to its angular size. So we're in agreement. It's just I'm not agreeing with you that we're seeing curvature in this image.
Okay. So now, where can you pull that image back up for me?
Yeah, give me 1 second.
So that I can, yeah.
1 second, my friend.
And then I'll probably have to buffer into it.
No worries. I just got it up. It's on
YouTube
the.
It's really behind, man.
Yeah, I see that. I got it on my phone over here, so I'm just keeping tabs. But hey, I do appreciate everybody tuning in. Let me go ahead and shout out just a couple of the regulars that are on here. We'll start off with the YouTube. We got Jesse Palmer, Big Pine Sailing, Matthew Shits. I probably said that wrong. No, I did. I said it correct. Matthew Shits. Awesome. Daryl Patton, Riley O. Appreciate all you guys being here, chatting it up over on the YouTube. Let me go ahead and head over to the Rokfin. Shout out to everybody chatting it up in there. We got John Osborne, Mischief Brew, and it looks like that is all we got over on the Rokfin. Thank you guys for being a part. And folks, over on the YouTube, if you would, it is completely free for now while we're live. Go ahead and head over to the Rokfin. They actually pay me to do this. So go ahead, create a free account, and chop it up in the chat. You can have your comment read live right here above me. So, again, I appreciate everybody tuning in. Hopefully, Adam has had enough time to go ahead and buffer in, as he said, and go ahead and take it away.
Yeah.
Awesome.
So that's I disagree with you on. I disagree that you can't see the curvature. I would like to know how far outside of the mountain that city lies. What city is this that we're looking at?
Give me 1 second. I don't remember right offhand.
Because this would mean that the city is built mountain, like right as the base of the mountain starts. So I do believe that the actual horizon that we're looking at is the top of the like actual city, like the sky, like skyline, and then back behind that, however many miles it is from Mount Jacinto, would be the determiner for me on it inside of this picture or not. Because as this picture stands, it just looks like the city's built right at the base of the mountain, like as soon as it starts.
Problem is, there's multiple cities. It is zoomed in pretty far, so I'm going to assume that it's the city right. Is that a city? I think that is. Yeah, it's San Jacinto. Literally San
San
Jacinto.
Jacinto.
It's
Okay.
it's pretty close to the mountain compared to the observation point. But again, let me go ahead and drop that link in the chat as well. That way, everybody can go ahead and, as they
Now,
say, do it yourself, right?
is that referenced on the actual picture, or
Yes, everything's referenced. They're very
okay?
they're detailed in these videos. Let me go ahead and copy this link. Alrighty. And put it in the chat for you guys to start over on the Rokfin. Boom.
Let me go over to the terrain.
Alrighty, and then let me
I'm
go.
gonna do this.
You're totally fine. Just a short little break, folks. Apologize for the dead time. So we're gonna go ahead.
Yeah, I apologize also. I'm just trying to, because I am trying to agree with you. If we can agree on something, I'm trying to agree with you.
Awesome. Yeah,
So I want to let that be known.
We're going for a full conversion tonight, folks. As they're going to either prove they're either going to prove curvature, or they're not. So it's going to be pretty simple. So let me go ahead. I got to get back to my channel here. Everything's so slow on my computer, it's ridiculous. So, folks, over on the YouTube, if you're really just hell bent on not going to Rokfin, and there are some who are, you can still support me by going to either my Cash App MrTribune, or you can go to Buy Me a Coffee if you care to support the show. And that way, I promise all the funds will go towards better equipment. That's literally first on my list here. Let's get into the chat. It's taking its sweet time. Hey, Waterworld made it in. Nice. Everything's so slow on my computer, it's ridiculous. Finally got that in the chat. YouTube, if you're really just hell bent on not going to Rokfin, and there are some who are, you can still support me by going to. You got the thing playing. If you do
Oh,
that,
sorry.
buy me a coffee.
I apologize.
You're fine. If you can mute yourself, that's fine. And that way, I promise all the funds will go towards better equipment. That's literally first on my list here. Let's get into the chat. It's taking its sweet time.
Is it still playing?
Yeah. Yes, it is. Hey, Waterworld made it in. Nice. Everything's so slow on my computer.
It's not even on my screen anymore.
Oh, nice. That's probably on your end.
Did it cut off?
If you're really just hell bent on not going to. Oh wait, is that on mine? I hope not. Support me by going to.
I'm freaking out right now, man.
That's funny. Ghost in the shell. All right, yeah, I got it, guys. My bad. I had it up when I did the chat.
One more quick question: does he have a referenced site?
Yes.
Not the height, but the actual site that he took the picture from.
Yes. I don't remember what it is right off the top of my head, but that's why I'm sharing the links in the chat.
Okay, all right. I'm scared to go back over there now.
Oh, good. Nice. Looks like we got some people over to the Rokfin. That's awesome. Appreciate you guys. Much love. Oh my goodness, it's still on that screen. Whoopsie daisy. A lot of people in this community are really familiar with these observations, and that's why they're, because we've been looking into this stuff for quite a long time, so it just doesn't make any sense, and again, if we just go back to what the math actually, what we can agree on, if we can agree that there should be at least, 2,600 feet of curvature due to this bulge, and we're still seeing most, if not all, of the mountain, that's definitely going to be a problem. for the Earth curvature calculator there. And unfortunately, I just don't think it's something that refraction is going to be able to save. Even with the standard refraction, it still came back with the bulge of like 2,000 and like 6,800 feet missing of the actual object due to that full math. When you take in everything into account, the reduction in angular size of the mountain comparative to the bulge, because the bulge again is halfway between you and the observation, the height of it. So although you're right, things do shrink relative to position. The bulge and the mountain are not going to shrink at the same rate because the mountain is twice as far as the bulge, because the mountain is what we're viewing. So the bulge is definitely going to appear closer to its true size. There's just no way you can argue that. And on top of that, again, we're seeing almost the full mountain. If you zoom in on this picture, you see that there's actually like it looks like there's like treetops that you can see at the base of the mountain there. So it's like we're seeing trees. We're seeing a mountain ridge that is at most like 2,000. A mountain range that's 4,000 feet high at most. And yeah, so again, this is just the first observation. We haven't even gotten into the Rock Lake observation. That one's going to be even harder. That is a 1 foot observer height, 8-mile observation, and all of the lights appearing in a straight line. I mean, that's going to be pretty hard to come up with an explanation for, right, Adam?
Yeah, it's true.
I appreciate your honesty.
So I did want to make one more reference to the Sagitta. Can you hear me? Am I muted?
No, you're fine. Go for it.
Okay, I thought I was muted out. So when I first started, because again, man, a lot of the videos that I see, they're extreme. They are compelling, man. They're all like, oh, well, why do I see that? If that's what it says, well, why do I see it? And I think that sometimes people don't take the time to understand, and maybe they don't want to, or maybe they just don't really care, or just whatever the case may be. And immediately it's like gears in my head where it's just like, I want to know. That's something I want to know. And I don't want anyone to tell me either. I want to at least attempt to derive something and figure it out, because it's one thing if you're told it and you memorize it, and it's another thing if it's something that you truly discover, you'll never lose it. It's something that'll be with you forever. So the goal is discovery. The goal is to get out and, even to your community of people, the goal is to get out and make your own observations. And just like people in the science community, they get out and they make their own observations, and they continue to do them, because there are a lot of failures in experimentation, and sometimes they have to be recreated or redone, or you have to go back to the drawing board and just figure out what's going on. There's going to be trial and error, and then there's going to be a learning curve to doing something that's brand new to you. And you have to understand that. So don't give up on my uncle told me, ask big questions, you get big answers. So don't give up, but also don't be afraid of the answers that you get, because if they are true answers, they won't go away. They'll stay with you. So I was talking to him when I started the equation, and how I started deriving it differently. I started deriving it from a ball, and then making my cross section and making a square. And then from that square, I derived what the diameter was, and I found a square plus b square equals c square so I knew all of what the sides were. And then I was able to subtract the hypotenuse from the diameter and then divide that area by 2. And then once I did that, I just kept doing the same thing over and over and over again, all the way until I could go as far as I could go. And I spent hours on it. And probably about like the second hour in, I said, I wonder if I'm wasting my time or not. So I ended up calling my uncle, because my uncle is the only person that I could think of that understands like a high level of trigonometry. He's an inventor and he's an engineer, and that's really what he does all day. So I called him up and I sent him a screenshot of what I was looking at, and I said, "Hey, can I keep doing this? Will this work?" And he said, "Yeah, but there's an easier way." And then he starts talking a whole bunch of trigonometry, and I'm just like, "Yeah, well, that's the whole point. I don't understand trigonometry." So he said, "Yeah, well, your way of work is just going to take you a long time, but also you have to realize that he told me this is the only what you're doing is the only geometric way that I can think that this is doable, right?" And then he told me that he can solve a couple of different ways, whatever. But the case is that he's smart and I'm stupid. I'm just an average guy. I do a lot of algebra, a lot of geometry because of the work that I do. It requires me to square buildings and level, and it requires me to do a lot of basic geometry. But I don't understand what he understands. So that's kind of like the whole point of trying to do this in a geometric way to where I can understand. And even when he plugged his numbers in our first go around, he said, "Well, um, you have to convert your degrees to radians and you have to do this." And he gave me some formulas to work. And then I worked those out with a calculator and was kind of like, okay, is this what I'm looking at? And then he's like, well, and then, it wasn't right. So he was like, huh, I got to think about this. I don't know. I don't know why this isn't working. And we kind of went to the drawing board and, he was talking out loud and, I was just listening and just kind of just there. And he said, I'm going to think about this a little bit more. We get off the phone. He wakes up in the morning and he says, I can solve this a couple of different ways, and then he tells me, but my biggest question is, I want to know why, if I'm standing at a shore and there's a boat right next to me, and the boat goes out into the horizon, why does it look like it's going up before it goes down past the horizon? And it really didn't sink on me. And I was already doing arc and chord measurements, but I had never seen it until he told me that. And that's when it hit me. Oh, they are going up before they go down. There's a bulge there. So that helped me see this in kind of a different light, to a place where, they are going up. There's a big bulge and then they're going down. So if we can calculate that bulge, that's kind of why I'm so hung up on it. It's because to me, it is that. Like, that's what it is. Now,
Are you willing
on
to
this,
are you willing to accept that that phenomena that you just described is an optical effect and not a physical phenomenon, that this can easily be demonstrated?
I don't know. I don't know if I'm willing to accept that, for the simple fact that um I see it visually in my head and also I see it mathematically in my head. But I would like to see whatever you have to show. That'd be awesome. I'm totally down for it.
Sure. Well, the first thing is, and I showed it early on because I knew this would come up, is the actual refraction, that actually looks like when we have a density gradient and light shooting through that, what it looks to an observer. And the thing is that it actually creates that sinking effect that you're describing. Now, not only that, there's another video that I can pull up, and I actually think that now's a good time to do so. So let me go ahead and do that.
Can I ask a question because that the second video, or that was the third video?
So this one I haven't,
The se-
or sorry, that was the third video. That was the last one I showed.
okay, that was the one with the laser going through the water.
Right, through the two fish
Okay.
tanks. Now the thing that's important with that is that he starts off by shooting it with no sugar in it, right? So there's no gradient; it's all the same median, and you can see that the laser's going straight. When they add the
So
sugar to the water, it makes it denser. So
that was one of the reasons. That was one of the reason. That was one of the questions I had. Why did he add the sugar?
to create a denser median.
Okay. All right. So, and then another question is, why was he shooting it through the water?
Because that's how we view through the atmosphere. We view straight out. We don't view. That is exactly how we view. We view straight out. So we're pointing the laser straight to also show what the light in fact does as it goes, and you can see that it does bend downward, which is exactly what you guys claim refraction does, that it bends the light downward. So there's no disagreement on that point. Where we would have to disagree, if you want to hold on to the ball, is that the refraction is causing us to be able to see further behind the bulge, the Sagitta, that's creating that effect, when in fact it actually kind of creates the opposite. What happens is you actually do see some raising. So this is like kind of what we see in real life. We see the ground rise up like you just described, and then once it gets to a certain point, we see a sinking effect. They took the same picture of the boat in the experiment, although it's hard to see, and they actually compare it. So you can see here, it's the same boat, it's the same distance, everything's exactly the same. The only thing that's different is the median that they're viewing it through. Sugar water versus regular water. And what
Right.
happens with the denser median when there's refraction introduced is the actual, the horizon rises up slightly, and the boat, although it appears a little bit at the same, like kind of almost at the same level, maybe slightly lower, the actual boat itself is compressed. And it literally makes it, you have to go and look at it. It literally makes it look like it's sinking on the horizon. Not only this, but this can be demonstrated with Rob Skiba's experiment, where he takes a Fresnel lens and then just slides the cardboard cutout of the sun back. You literally can see the sun drop, and you can see, basically whatever's moving further back, it just drops. So it's pretty interesting effect.
So my biggest issue with that video would be the fact that we're adding sugar to the water. I don't know what that would do in the atmosphere. Like why would that reflect what the atmosphere is doing?
Right.
So that would be the issue that I have with that video. And then also, we're looking through molecules of, air molecules, and some places are more humid than others, but some places the air is extremely dry. So I just have an issue that we're shooting light through water as opposed to above the water. So that would, because light will refract anything, or water will refract anything. So you drop a pencil into a cup of water, whether it's got sugar in it or not, and look at it, it's going to be refracted off to the side.
That's actually because of the curved lens of the cup. It's actually this is one of the things that Globers actually put forward a lot when they say that we don't understand refraction and how it works. They actually say that it can magnify in the water, but it's also mostly refracting through the glass. And so that's how you're actually able to take two arrows that are facing the same way. You pour in water, and you slide the circular glass over, and it makes it look like the arrow is facing the complete opposite way. Same effect with the guy who's in the swimming pool. There's a video going around, and his head looks like it's completely separated from his body.
Right.
It looks crazy. But that's also an optical effect due to the curved glass.
I showed my son a demonstration of refraction with a fishing pole inside the water with no container or anything like that. And it'll do the same thing. It'll bend it. It'll make it look funky. Same thing with the fish. When you see the fish in the water, they look huge. Then when you pull them out, they're these little Twinkie minnows.
Nice.
So that is, again, the laser through the water would be my biggest obstacle to overcome, and then adding the sugar to it. I understand that it makes it dense, but you're taking a natural environment, and then you're adding a control substance to it. So it's really cool that it does that, but I don't think that it's an accurate representation of what we're of the atmosphere that we actually live in.
I'm so
So that
happy to
would
hear
be
you. I'm so happy to hear you say that. And the reason why I'm happy to hear you say that is because this is actually like one of the closest, best examples that exists of refraction and refracting light. You cannot provide me an example that shows me that refraction makes it so that we can. I'm hearing a little bit of an echo, but you cannot show me that refraction is actually causing us to be able to view just a little bit beyond the horizon, the way that it is claimed. Now, we have a demonstration that we can show that it causes things to appear to sink. And there's another video that I haven't shown yet that actually shows the horizon rising and falling throughout the day based on the atmospheric conditions. So I actually do believe in refraction. I believe it bends the light up and down depending on the conditions. But um, you don't have a demonstration that shows that it can justify for any of the observations that I mean, any of the ones that I've shown tonight, even for the Mount Jacinto, for the 8 Mile Rock Lake frozen laser experiment. Sorry, not laser, frozen lake experiment. Um, pretty much all that you have been able to show is just the way to derive the math. And don't get me wrong, that's great for checking the way that the math is done. But we have a calculator that's really, really accurate for that. And the thing is that we're still coming up with observations that do not meet that calculation. And so you did
so.
say earlier
Go
that you
ahead.
disagreed, that we actually are seeing curvature in that image. If you could demonstrate that, then I'm definitely open.
The curvature in the Mount Jacinta image.
Yeah, or the Rock Lake one, either one.
Okay, so the Rock Lake one, the only the only rebuttal that I have for that is well, first of all, let me address something that you said earlier, because I do want to agree with you again when I can. Um, I don't have any demonstration of how refraction works. Even if I did, I wouldn't have it right at hand. So, and I don't know enough about refraction to really, again, I'll try and talk about anything. And the reason why I'm commenting on it is just to kind of give you an understanding of how I'm perceiving it, and kind of like I am trying to process this really fast. So we're talking about it, and I'm trying to process it and just kind of be like, these are the questions that are raising to me, and these are the things that I would have to ask towards other evidence or towards other experimentation, um, whoever it's from, whether it's from the science side or the True Earth side. It doesn't matter, where one can provide it. So that's that with the Rock Lake.
You're kind of cutting out a
It's
little bit.
extremely weird. Can you hear me?
Yeah, go ahead.
I did turn my thing down because you said you were hearing an echo. So thank you for reminding me. Did that go back up?
Yeah, you're good.
Okay. So the Rock Lake experiment, my calculations would show 10 foot 8 inches of curvature. Point blank period.
For the Rock
Now,
Lake, right?
Yes, for the Rock Lake, there should be a 10 foot 8 inch bulge. So I don't know. I don't know what's going on. I don't know how refraction would work in a cold environment like that. I don't know if you would be able to see that at 8 miles. Also, I guess my biggest question in that demonstration is, has it been recreated multiple times?
I believe that
So
was
because
I believe that was the third time that he's done it.
Okay, all right. So, and is it a credible source? So those are the questions that I'm asking. So, on a science base, which again, don't get me wrong, I'm not all science, because I believe in some funky stuff too. Now, but on a science base, a science will require a controlled environment, and they'll require that it be repeated, 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 repeated. It's something that can be repeated,
But
and it's
where
something that can be. What's that?
I'd hate to cut you off, because I do like to let people talk, but I do feel like this is important to address because I feel like you're given a pretty unfair bias to our position and not applying the same standard to your own. Because the fact is that you currently, if it's true that you still believe, if you're hanging on to the ball, you know, you do believe that basically on the word of the so-called science without, from what I've seen so far, without observable, repeatable, demonstrable evidence. I've been able to show you experiments that can be recreated. They're at places that anybody can go and check, and they're being recreated all over the place. You know, so that's actually one of the things that I hope to be doing here soon is adding to that with some mirror observations down over in Tampa. So I think that that's going to be really helpful. Um, so
Yeah.
so you would, even if we do provide evidence that, hey, we're seeing way too far, and we know this would happen because it already did. It's like, hey, we see way too far. Oh, that's just refraction. I was like, okay, you don't know anything about the
No,
variables of the day. uh,
no, that's not what I'm saying. And I do want to clear this up because I do think it's important. What I'm saying is I don't know what's going on. And it's worth looking into. That's what I'm saying. What I'm saying that by the calculations that I make, right, there should be a 10-foot, 8-inch bulge. Okay. And I don't know how much refraction will account for that. I have no idea. I know that refraction can do some pretty wicked stuff. We've seen it in pictures. Can we agree on that?
we can definitely agree on that, but the problem is that you will, although you're saying I don't know, let me just ask point blank. Do you believe that you live on a spinning ball?
I do.
Okay. So, with that being said, you pretty much have to either A, attack the source, or B, basically, you know, not to be insulting or anything, but you basically have to use the cop out that we've all heard, which is, you know, oh, that is interesting. But the thing is
Okay.
that, yeah, that is interesting.
Touche.
It
Touche.
is. But let's just assume it's true, right? If what we're saying is completely true and accurate and the observations are recreated and you can recreate them, if all that is 100% accurate, what would that mean for the curvature to you?
Um, so I think my first response to that is I can't I can't throw out a mountain of evidence based on one experiment, right? Unless and even you know sometimes people let's say if I go out and I do an experiment because I I could be wrong with this math right here, right? You don't know, I don't know, who knows, right? It checks out, I can cross reference it, but I could be wrong. But no one could tell me that that math is wrong because I did it. So there, even if I went out and did an experiment, right, and something, whatever happened, whether it was for or against either of our claims, right, I am always going to have a bias on the experiment that I do because I conducted it and I saw it with my own eyes. And this is how religion works as well. So if we see something and there's it's unexplainable, we give it towards a certain thing, right?
God of the
So what
gaps.
I'm saying is, what's that?
God of the gaps, as they say.
So right, you are saying, okay, I can't explain this. This is what it must be, and I don't think that that's a right approach for either side, for your side or for the side of science. And again, I separate myself from the side of science because I don't agree with everything that science says. Though I do agree that we live on a spinning ball, I don't agree with everything that science says. So in that instance, I don't know. I do not know why you can see those lights. Can it be explained? Because to say that flat Earth is the only thing that can describe it,
I can explain
that's
away. The problem with your reasoning is that anything can be explained away. As someone who works in sales, I deal constantly with people, and I can give somebody infinite reasons to buy or not buy something. That's just the honest to God truth about it. So, my follow up question to that would be, how much evidence would you need to be able to say, okay, maybe I don't live on a spinning space ball?
hmm. Um, as much evidence that the globe has provided.
So let's get into that then. What demonstrable
So
evidence does the globe provide?
let me backtrack to something you said though about everything being explained. I do believe that everything has an explanation, but I don't believe that science has the explanation for everything. So, and I don't think that we'll ever have the explanation for everything, right? So, and I mean just people in a whole. So, I do believe that there's an explanation for everything, but I don't believe that science has the explanation for everything. So, I just want to agree. I don't know what you were exactly getting at there, but I do want to make my statement on that. That I do believe that everything can be explained.
Oh yeah, sure. I believe that too. I just don't believe we know the explanation for everything necessarily.
Yes,
So
yes,
I'm in full agreement there. I don't use religious arguments when I'm talking about these kinds of subjects. I don't do the God of the gaps or anything like that, or it's unexplainable, therefore it must be flat. That's not what we're saying. The thing is that, and this is again where we go back to where we agree. We agree that if nobody ever told you that you lived on a ball, you probably would not come to that conclusion, right? What we see and observe is a flat stationary plane. And the only real piece of evidence that is offered towards the globe side that is even somewhat tricky for the flat Earth side to explain is the southern star crux in rotation. Basically, the layout of the stars. That, even though it is the best evidence the globe has, it's still very weak on its face because we don't actually know the true layout of everything. We have a general idea, but the thing is that, and you don't have to take my word for it, just look up, you can Google how often does GPS get things wrong? And the answer is all the time.
Oh,
Yeah,
I mean, has anybody ever owned an iPhone?
for sure. It gets things wrong all the time. All the time. It gets the distances wrong. They often come up short, I'm realizing, as someone who I usually build routes and I'll go drive those routes, and I find that the route is often short than what it says, which I think is pretty interesting. But I digress. With that being said, there's also the shoreline paradox. We have four different countries that have put a measurement on the same border and got four different, or not the countries, organizations from different countries, and have gotten a different measurement for the same border. This is a very real paradox. You can look it up. Just Google shoreline paradox explained, and they will tell you that it is basically impossible to tell you the true area of the continents because the outline is always changing based on what unit of measure you're using. So if you're gonna divvy it up by every 2 miles, you're gonna get a different answer from someone who divvied it up every 5 miles or someone who divvied up every mile.
Right.
So, and it's really crazy how they can come up with wildly different numbers. Like one was 20,000, another was 140,000. Like they were way off. They weren't even close. So that is something that, we don't really know the true shape or layout of the continents in relation to each other. We have a general idea, and we can get there because the ground towers and the satelloons all bounce the signals to help triangulate. But you can just correct and augment that to a globe, and nobody would ever know. So my point is that when we look around, we see and experience that it's flat. We have long distance observations that show that it's flat. And these are, even though I could show more, I wanted to take some of the best ones. That way we could come to the most common ground. And if you can acknowledge that what we are seeing in these observations does not match the math, then that obviously means that the math does not work. And that's not my math. That's not your math. That's just the math derived however many different ways you want to derive it. If the math doesn't work out for even one of the observations, really, that's why it's called a black swan. Everybody in the world thought that all the swans were white until one person discovered a black swan, and then we realized it was just rare. So we are considering all these optical phenomena as a result of Earth's curvature when it can be actually demonstrated to be light effects, to be refraction, because we do live in a atmospheric or a atmosplanic gradient, and we can demonstrate this by just looking at the moon and the moon and the sun on rise and set. if you've ever been to a Florida sunset, then you know that the sun gets really, really huge on the horizon. It's huge. The sun's not
Yeah,
literally that
sometimes, yeah.
close. It's being magnified and refracted through the atmosphere plane. So we have demonstration that the observations can work on a flat Earth. I'd like to know the demonstrable. What is the best evidence that you have that leads you to believe that despite all these observations, you still live on a ball?
Okay, so you said something a couple of minutes ago about that if I no one told me that the earth were round or anything like that, that I would never think that the earth was round because everything, everything it feels like we're stationary,
Well, how would
right?
you? Well, not even just that it feels like we're stationary. It's that you. How would you even derive the radius from nothing? The core of your whole math actually depends on an assumption outright. And so without that, you really don't even have a basis for your model. It's just pure assumption.
Um if I assumed so without a radius, you would need a drop height, right? Between the arc and the chord. So if I had a distance, I could probably let me see how I would do it.
Well, if you're going to do it by chopping an orange and still using a ball with a radius, then just acknowledge that you still had to assume a radius. Let me tell you how the
Well,
people used to do it
if we
back in the
did have
day.
the drop height, we could figure out what the radius is. That's what I'm saying. So I don't know how I would work that without anything. I don't know.
But you could just call it.
I'm
You could call it, instead of drop from curvature, you could simply call it drop due to reduction in angular size to the observer.
well, the drop height that I'm talking about is between the peak and the bottom chord. The chord is an imaginary line. It's just the distance that
Right.
we're
So
plugging into the
in order for there to even be a chord, you have to have an edge of a ball, right? So you're assuming a ball to even
right.
assume the chord. There's another way to calculate distance that I don't think you've ever heard of, and it's the way that the sailors used to do it back in the day. I highly advise that you look into celestial navigation, because there's a way to draw the triangles using the sky as the top of the triangle and assuming that you are on a flat topical plane, or topographical plane. Sorry, misspoke.
Right.
So if you do this,
So
you can do a squared plus b squared equals c squared, and you can derive the distance between you, an object in the sky, an object on the ground, and you can come up with the correct distance. And we know that this works because that's literally how sailors did it in the 1400s and 1500s.
wait. Hold on. You gotta say that again.
So
You
Captain Magellan, Cook, these famous sailors who had to be able to navigate the earth and be able to navigate correct distances, otherwise they would plot their course wrong and starve to death on their boat, which did happen from time to time. They basically used I'm trying to think of the name of the tool. They're a sextant. They basically use a sextant to get an angle of elevation between them and an object in the sky, let's say the sun. And then they assume a straight line between them and the horizon directly beneath the sun. And from there, they can calculate a very accurate distance. But it depends.
okay? So
It depends on a flat plane.
and this is called celestial navigation.
Right. But you do have to look into
Have
the older
you?
sources, because they've recently now changed it to be, well, the change in elevation of the stars is actually due to the Earth's curvature. But if you look back at the older works, that's actually not how they saw it. They actually, I can't remember the actual source. I'll probably check the chat and someone will have it, of the person who said that when push comes to shove, all models aside, when life or death comes to it with navigation, we assume that the Earth is a stationary plane and that the sky is a moving shelf above us. So that's the only assumption that actually works to correctly derive the distances when you actually go to check it.
So I'm sorry, my brain it's going right now, and I'm trying to stay on topic, but it's just like, but I am gonna try and I am gonna try and stay here with you. Have you heard of trigonometric parallax.
I believe so. That's where you're looking at objects move different in relation to how far they are to you.
No.
We'll go ahead and explain then.
It's a so if you take your thumb out, right, and you look at your thumb and you close your left eye, and then you close your right eye. Let's say you line your thumb up with a corner in your room, okay, and you close your left eye, close your right eye, and your thumb will look like it's in a different place.
Right, that's exactly what I'm talking about. That's parallax.
Okay, all right. Okay, so this is how they measure the distance and the location. This is the basic concept of how they measure the distance of stars and planets and things like that.
They're using arc lengths,
So
and they're measuring it in degrees
no
based on
arc
the angular
lengths.
based on the angular size of the object.
No. What they'll do is the Earth isn't big enough, right? If you go to one side of the Earth and then you go to the other side of the Earth isn't big enough to get an angle that matters, right? So what they'll do is now, and this is in the globe model, of course. The Earth will rotate around the sun, okay? So when the Earth rotates around the sun and it gets right here, I use this as an example.
Well, that's
it gets
another.
right here.
Just so you know, that is another assumption. You're assuming that the sun.
Yes,
the Earth
yes.
moves around the sun.
Well, I am explaining the scientific method that was explained to me.
Well, just so you know,
So
science, again, you have to have an observation. It starts with an observation, and then it follows with a question, and then an experiment. So just keep that in mind.
okay. I think that we'll be able to touch that later in the conversation. I think that we'll be able to kind of knock this same topic, and I don't know how long it'll take us to get there, but I think that we'll get there.
Give me just 1 second to do a quick shout out, because I saw some more people in the chat, and I just, I really appreciate all the love and you guys being here. This has been a great conversation. We're really hammering it out. So again, I do appreciate you all being here. Mellowdome, Sedetic Warrior, and all the others. So let's go ahead and keep things rolling on. I do want to go ahead and give the 15-minute warning. We've been on since 9 o'clock or so. I feel like 2 hours is a pretty good amount of time to stay on YouTube. So we're going to go ahead and move over to Rokfin here at the top of the hour at 11 o'clock. So if you guys haven't had a chance already, be sure to go to it in browser. Don't download the app. The app sucks for now. They're working on it, though. So go ahead and head on over to Rokfin here within the next 13 minutes or so. We'll continue the rest of the conversation. I don't know how long we're going to go ahead and be into this, but we're getting into a lot of great topics, so I definitely want to keep the conversation going. And Adam, if whatever point that you were about to bring up, if you would go ahead, because I honestly forgot what we were just talking about.
Sorry, I gotta get like Dave, man. I gotta get better props, man. Dave had some good props. He had them right there, ready. So again, this is what was explained to me. Okay, so we have our sun, okay, and then we have our Earth, and our Earth circles around the sun, right? It does like an elliptic orbit. Okay, so when the Earth gets to a certain point, they'll take a measurement to a star. Okay. Matter of fact, let me share my screen. I can draw it out. Yeah.
Just so you are aware, also, the new Tychonic model of the universe does fully explain parallax and basically all the sky observations perfectly. So even though I know your model can work, it's still not evidence that it is in fact the truth.
All right. I should have picked a bigger eraser, eh? All right. So let's say we have our gas giant. Okay. This is the sun. And then we have our Earth. And then out here we have a star. Okay. So when our Earth gets to one side of the sun, we stretch out an imaginary line. And then in 6 months, when our Earth gets to the other side of the sun, we'll stretch out an imaginary line. So every triangle has 180 degrees. So we can measure these degrees, right? And we can triangulate. And again, this is something that I don't fully understand. I'm just doing this based off of memory. So we can triangulate
You can't derive
the
that.
angles. What's that?
You can't derive that.
No, I cannot derive this.
I'm just messing with you. Go
This
ahead.
is something that I cannot do. Yeah. So we can triangulate the angles and figure out the distance to what we're actually looking at. So this is a rough I do not know how accurate this is. I should say I do not know how accurate this is. I saw something on the Mellowdome the other day, and it was talking about how we're 20 to the 100th power or something, or 120 million to the 100th power or something off. Like it was like this incredibly high number with like cosmology and astronomy. And I don't think that I don't think that it's something that we'll ever fully understand or ever have a true model for. I don't.
Perfect.
Honestly.
So then we can agree.
Unless we.
So then we can agree that our model doesn't have to explain every little thing in the universe then to still be more accurate than the current one.
No, I don't think that you have to explain everything. No, not everything needs to be, what's understood doesn't have to be explained. You ever heard that?
Yeah.
Yeah. So it's like I don't think that everything needs to be explained, but in the same sense, there is a lot of evidence, and I won't say proof, right? But there is a lot of evidence that leads you up to a place of understanding. So I may not ever think that I live on a spinning ball if no one ever told me. But at some point in time, humankind did. So man as a whole, we started looking around like, that's weird. And it started by looking up. It started by looking at the stars and at the that was the first thing that I noticed, because I just got my telescope. Like I got it on Saturday. And have you ever owned a telescope?
Yeah.
Okay, so do you remember the first night you hooked it up and how frustrating and difficult it was?
Yeah, I couldn't see anything.
Yeah. Do you remember the second night you attempted it? How frustrating and stupid and difficult it was?
It took me like a week.
Yeah, and so it's the same thing. Like today, I finally got like I finally got everything adjusted on it and calibrated on my and on my my looking site, right? And it was working out perfect earlier when right when I got home off work. I said I got to do this in the daytime. I got to adjust my my looking site, and it wasn't until someone told me how to do it that I was like, oh, okay, this is easy. This makes sense. It's not that, it's not that difficult. And then I applied the knowledge that he gave me directly to my telescope. So it's okay to learn from people. It's okay for someone to tell you something and then you apply it. Now, my issue that I have, and this is these are experiences that I've had ever since I started looking into the flat Earth model, is that people will send me certain videos and then I'll put them under scrutiny and do a test myself, and it's not at all what they said. So Austin sent me a couple of things a few years ago, and I did some cross-referencing, and it was this was more biblically based, but he told me this is what the Bible says about flat Earth, and this is what this, and I went and looked, and it's not anything what the Bible said. Not even like barely words were lining up. So I had a big issue with that because here I am, I'm putting the work in and I'm going out and I'm doing the research. And now I feel like you've been telling me that I've been lied to. And now I feel like I've been lied to because this is what you sent me. And this isn't what I see. And this isn't what's in there. So like in a few things, they go by and I see all this mountain of evidence. And then when I put it under a little bit of scrutiny and I, try to understand what's going on, oh, okay. And again, I don't think that you guys have reasonable questions, man. I'm telling you, even the video that I watched earlier, who the freak wouldn't question that, man? 8 miles. There's supposed to be X amount of, who wouldn't question that, right? I'm not telling you that the questions are stupid. That's not what I'm saying. These are real questions that should be answered. And I was trying to really touch on that at the Mellowdome and really just I don't think the science is doing a just job at addressing some of the questions. Now, whether or not, people get, arrogant and back and forth, I really don't want to be like that, man. So at the end of the day, I do think that science should step up and they should try to address more questions that people have about the curvature of the earth, especially if we're going through um a period where people are being drawn towards the flat earth,
You don't
right?
think it's
I do think
you don't think it's weird that they're censoring it?
um yes and no. Yes and no. So I think that if someone's talking about the shape of the earth, that that you should have the freedom to speak, right? But in the same sense, I do think that certain things, and I'm not saying that this is one of them, because I could be 100% wrong and you could be 100% right. You know what I mean?
100%.
So my evidence leads me in a direction and your evidence leads you in a direction, right? But what I am saying is there are within the flat earth community, there are a lot of people that are just head first into conspiracy. And there's it's like all of this conspiracy about and there's a lot of weird stuff, right? So I don't know how healthy that is, right? Also, I don't know if you should shut someone up, right? But then again, if something is privatized, right? I'm a business owner. If I don't want somebody talking about something in my platform, I'll kick them off of my job. This is my job site. Get out of here. I don't want you talking about that.
Right,
It's
right.
inappropriate. We have kids working here or just whatever the case, So if YouTube and all of these different organizations are private and this isn't something that is, they have the right to choose whatever they want to do. So you can't take away their freedom either.
So I agree with you
So
on that, but my question was that isn't it weird? I mean, if it's so stupid and so
um
easy to prove, then why are you shutting it down? I mean, just debunk it and be done.
so yeah, I agree with you. It is, but I don't think that is from the side of I don't think it's YouTube's job to debunk anything, right?
So the problem is,
Um
the other thing is that, and the reason why this is pertinent is that it's not actually these private companies that are making the decision to censor it, and we're kind of getting into Rokfin land. So everybody gear up. In 3 minutes, we're gonna go ahead and play a little intermediate clip, some more music, and then we're gonna kick back up with part 2 of the
yeah,
True Earth
how
debate.
long will the break be? Because I gotta go to the bathroom.
Oh, you'll have
We'll have
plenty of
enough
time.
time.
You'll
Yeah,
have plenty of time.
awesome.
You will have plenty of time, my friend. So
let me scribble down where we're at right now.
sure thing. But essentially, man, I just completely lost track of where we were at. We were just talking
We
about
were on the we were talking about, don't you
oh yeah,
think
the
it's weird
censorship.
that they're censoring? Yeah.
Yeah, so it was literally, this isn't a conspiracy. This isn't fake news or anything like that. This is easy to verify. The I can't remember her name, but somebody who was one of the head runners of who was responsible of determining what's allowed and what's not allowed on YouTube was actually pulled into Congress, and Congress, our government, told them, hey, what are you going to do about these flat Earth and 9/11? And they named off a couple other types of videos, but flat Earth was right in there. They named that specifically. Why is the government giving a shit on what YouTube allows on their platform? Especially when it's just something dumb like the flat Earth, right? If it's so stupid, don't you think that's a little weird?
So I think it is probably the same reason why a lot of flat earthers pull their kids out of school. They don't want their kids to be indoctrinated. And in the same sense as, so the majority will rule. And if you have the majority of people, and again, these are regular people,
Nice projection.
they have no, what's that?
If you're saying something about the majority, the globe's the one that relies on majority rule to remain to make it seem like it's still true. I definitely feel like I've presented more demonstrable evidence than the globe side at this point, just to be honest with you.
Well, I am here to my views and my opinions on the knowledge that I have, because I'm an indoctrinated child too, right? So my entire life I've been taught things, and I realized this when I went to college. My entire life I was taught things, and then when I got to college I unlearned them and learned a new set of things. You know how frustrating it was to find out that Columbus, when he sailed the ocean blue, he didn't come to America. That's that's like learning the Santa Claus isn't real. You know what I mean? It's something that you have to be untaught, and then I do have a huge issue with what they teach in schools, right?
All right.
So
I hate to cut you off. Hold your point.
yeah.
Hold your thought.
We'll continue.
We just hit the top of the hour, folks. I appreciate everybody who's been here so far, especially you folks over on the Rokfin, the YouTube, everybody. One love. But the truth is that I got to show the support to the people who actually will write me a check at the end of the month. So I'm going to go ahead and turn the stream off for YouTube, and we are going to kick it to the Rokfin only. And trust me, you're definitely going to want to be a part of that, because we're getting into all kinds of really cool stuff that we probably can't talk about over here on the YouTube. So with that being said, let me stall here for just 1 second here. I wanted one more song to play. I had some people in comment that they liked the song. Little did you know that that's actually written and I believe performed, right, Adam?
Yes.
By our guest here. So even though we do have differing views on the cosmological order of things, we can still agree on some good music, some good tunes. So Adam, if you would, you can send me another song. Send me a long one, like whatever your longest one is, as long as it's not like 13 minutes or something. Just give us like 5 to 10 minutes. And yeah, I'll go ahead and play this little clip for you guys, and we'll get right back to it with part 2 of the Tribune Show. So, Adam, I will wait for that to get sent over.
Yeah, I'll send it over right now.
Yeah, please in my email. That way I can just pull it right on up. All right, folks, remember, always do it yourself. Do your own research. Don't take my word for it. We provide plenty of resources, links in the chat. We're going to be getting into even more over on the Rokfin side. So everybody over, I hope to see each and every one of you over there. You do not have to pay for an account. You can create it completely free, and you will be able to chat it up live on screen with the gang. So please go ahead and head on over now. We are going to go ahead and get this outro going. Make sure you don't forget, YouTube, to check out TrueSmacks.com and the Flat Earth, Sun, Moon, and Zodiac app by Blue Water Bay. Don't forget to use your referral, Sky, for True Smacks and Tribune, MrTribune, or Tribune. Yeah, it's just Tribune, I think, for the Blue Water Bay. So go ahead and become a blue dot today, and we'll know who sent you. So let's go ahead, and I think he's still picking one out, but that's okay.
I sent it to you already.
Oh, okay, awesome. Let me go ahead and pull this up. YouTube, thank you once again. I'm going to leave you on the song, and then we'll go ahead and switch right back over. Repeated myself quite a few times, as some people like to say. When you repeat yourself, you will often find that you have plenty of time to pull up exactly what you need to pull up. You just have to repeat yourself enough times. So this song is called Die to Get There. and you can find that on Spotify and on YouTube. I think YouTube, right?
Apple Play.
Apple Play. Awesome.
Apple Music.
Yeah. So if you like this kind of music, go ahead and go check it out. Go ahead and leave it on play. We will be back here in just a few.
Everybody wanna get to heaven. Don't nobody wanna die to get there. Somebody told me that years ago. Something I ain't never hear before. 19, we were living reckless. Know it took a little time to get here. Mama told me years ago, son, you just need a miracle. Ooh, we were too young to understand. Shrunk in Wonderland, where love is lost. I'm a troubled man with a jealous heart. God, I got bloody hands, and I know that hell is dark and heaven's close, but we come from hellish parts. And selling dope, time will tell it all, but it never spoke. I wish I could see them all. I pray you don't let me go, but I know the people die. I do that when I'm old. I know that Peter lied and Rooster Crow. I know that Jesus died. Judas told, don't got all the reasons why, but I know the truth is gold. Through the fire and the flames, you are with me. Through the change, through the darkness and the rain, through the hardships and the pain, through the fire, you are with me. Through the darkness, through the hardships. Living in a world without water, all the rivers dry. Where the flowers don't bloom, they just will die. Ooh, yeah. Trying to get to God. Trying to get to God. Seen a man standing on Mary Camp holding picket signs. Say Jesus saves. You stay every day till it's dinner time. Go and lead the way. Take a leap of faith. Yeah. Fist up, brother, preach and pray. Ooh, we were too young to understand. Shrunk in Wonderland with a kill stick and a 40. Sitting in the hills clicking at Dorothy. True story. And we did it all for new 4Gs. Smoking Newports, who par me. And we had kids and bought car seats. Barbie dolls in the yard swing. RC cars on Christmas. Posted pics on Pinterest. My oldest son in Star Wars. My daughter thinks she a princess. You all girl, you go girl. Through the fire and the flames, you are with me. Through the change, through the darkness and the rain, through the hardships and the pain, through the fire, you are with me. Through the darkness, through the hardships, through the fire and the flames, you are with me. Through the change, through the darkness and the rain, through the hardships and the pain, through the fire, you are with me. Through the darkness, through the hardships. Everybody wanna get to heaven. Don't nobody wanna die to get there. Somebody told me that years ago. Something I ain't never hear before.